right, welcome everybody. I was given the impossible mission to give a short introduction, 20 minutes to AI and generative AI. And there's only one way of doing that in 20 minutes is I'm going to speak very fast. And so the first thing we would all agree is that AI is already here. It's been here for quite a bit of time, actually. It's in your car, it's in your smart speaker at home if you have one, it's in your phone, it's in your headphones. If you're using Google Maps, you're using AI. It's been in the news in particular since 2017, 2018, when AI systems started to have sort of superhuman powers, like beating the best Go players at Go. These days, you can use it to do extremely useful things, like outputting an image of a corgi wearing a hat on Times Square. And then there is ChatGPT, of course, since a little bit than a year ago, where all universities and schools are starting to wonder, are all our students going to hand out homework that have been synthesized? If you just go to Google and look for scientific papers and use the keywords as an AI, you will find today, I think it's tens of thousands of scientific papers submitted on the archive that have been completely synthesized by ChatGPT, and the authors didn't even care about removing the first sentence as an AI system I. And of course, the sometimes bonkers thing, like this was a couple of years ago in a semi-serious journal, The Guardian, where they were running an article about an AI being able to distinguish whether you're straight or gay just based on your picture, which is actually completely bonkers, right? As many things we see in the news. But this is sufficiently dangerous that it makes an impression on people. And it's very important to understand that at least a little bit, if you have no technical background, what AI is, what it can do, what it cannot. So that's what I'm going to do in the next 18 minutes now. All right, so the first thing you have to remember from this talk, if you have never done anything technical, is instead of talking about artificial intelligence, start thinking about something called machine learning. Artificial intelligence is anthropomorphic. It makes me think about people, about the human brain. We're talking about computers and algorithms, not people, not the brain. So what's machine learning? In machine learning, there is learning. And because there is learning, again, there is a reference to people. What we mean by learning in machine learning is something simple. Please note the color codes in the sentences. I will use them throughout the talk. Machine learning means optimizing or updating a model. I will explain what a model is with a super simple example. Based on a measure of success, you have to give it a task, something the model has to be able to perform. And based on training data. 3 ingredients, red, blue, green. Let's see that visually. A simple but powerful model is, suppose you collect data about people in this room, you ask them their weight and their height. It's going to be anonymous, don't worry. All right, so you are going to, my graphs are squeezed on the slides, I don't know why, but okay. So suppose you're going to report that on 2 axes. On the horizontal, you will have the height of people, and on the vertical, the weight. These are 2 persons. Usually, height and weight are correlated. The higher you are, the taller you are, the heavier you are, in average. And so if you start collecting data from 2 people, you'll see that. Now, a good model would be, of course, a straight line, because there is this correlation between being tall and being heavy. So in red is your model. This is something, an idea, a preconceived idea you have about the data. This model can be set with parameters. In this case, your model is a straight line. You need 2 parameters. The angle of the line, the offset with respect to one of the axes. So in red, you have your machine learning model, a straight line through your data. In green, you have your training data. If I have only 1 green point, I don't have enough training data to set my parameters. There is an infinite amount of lines going through 1 point. If I have 2 training data, then I have enough data to set up my parameters, and I can fit my model. Of course, the relationship between being tall and heavy is not perfect. Sometimes a person will be slightly heavier with respect to their height, like a little bit of me if I drink too much. So the point is going to fall out of your model, which means you have to update your parameters. So you're going to shift a little bit your line. It's relatively easy to do by hand. It's super easy to do with a computer. There's only 2 parameters. You have to nudge them a little bit until the moment the mistake it makes is as small as possible. Here, the measure of error is the distance from your new point to your new model. Compute that, you minimize this error by changing the parameters, and your model is becoming better at explaining the relationship between height and weight. All right, So machine learning is all about this single equation, somehow. It's about being able to emulate a decision. Here, what is the weight of people if I know their height, based on a preconceived model of this decision. You have to have this model somehow. It can be very generic. This model is going to depend on a certain number of parameters, here only 2. And in order to set these parameters, you are going to use training data. And then you are going to use that model on unseen data to explain the weight of people if I give you their height. Of course, this can be turned into more than just regression, but a classification. For instance, here, you could imagine that you have a population of 2 user profiles. The green users are, I don't know, the healthy ones, and the yellow users are those who have some sort of sickness. And then you have to fit a model that will separate this population into the right classes. Again, in this case, you could try to have a simple model, 2 parameters. Everything that is above the line is one class. Everything that is below the line is another class. But if you start having, oh, this slide is completely distorted, I don't know why. But if you start to have, more complicated data, you have to fit more complicated models. To fit more complicated models, you need to have more parameters. A line is 2 parameters. A red curve like this one is like 20 or 25. The more complex your data, if you want to have a model that can explain it, the more parameters you will need, the more training data you will need to be able to set the parameters. All right. Next ingredient. So we need models. The most powerful model we have these days, which you've heard of, is called neural networks. So what's a neural network? Well, it has hardly anything to do with a neuron. That's a technical term we use. It looks a little bit like a neuron. So again, sorry for the distorted slide. I don't know why they have shifted. But a neural network is nothing but a model. So it's the red part of my slides. It is something that will compute the average of the input data. So you have input, let's say training data in green, say pixels in an image. Imagine you have a computer looking at images and trying to detect if there is a human face in it, like you have in your computer. So in green would be the input data. Your model is everything that is in red. It's going to do something super simple. A single of these neurons is going to have, here in my example, 3 parameters, W1, W2, W3. It's going to compute just that single equation, an average of the input data. Right? It's going to run that average through a threshold, and if it's big enough, well, it's going to be excited and send a signal. Right? So it's a very, very, very simple model. That's going to be going to an output, and the output is going to be a decision, whether there is a face or not in the input pixels. So again, a neuron, in a computer science term, is something extremely simple. You can't do much things with one neuron, but just like in a brain, this is where the analogy comes from, you can start to network this neuron. So here is a slightly more complicated model now. Instead of 1 neuron in red, I have 4 of them. Each of these neurons have their parameters, and so instead of having 3 parameters that I have to play with, I now have 3 parameters per neuron, and as many parameters going to the output. So already with something that simple, you could count all the red arrows in this picture, and you would have a complex model already, something that you and I, by hand, could not compute the solution of. I could not guess by hand what numbers I have to put on each of these arrows to set up my parameters. But a computer can do that very, very efficiently. You can make this even more complicated. Instead of having a single layer of neuron, you can now have several layers of neuron. Now we are going into the territory of something we call deep learning. So we have many layers of these neurons connected together. Right? So a deep learning model is a model a little bit like this one. It has many, many, many layers of neurons, and each layer has many, many, many neurons as well. Since all these neurons are attached to parameters, in such a model, you can start now counting the arrows. You see that the number of parameters that you have, think of the parameters for my line, the number of parameters grows very, very quickly. And so instead of fitting a very simple model, like a line to your data, you start being able to fit an extremely complex model to your data. Because of that, this model can start modeling complicated decisions. There's a caveat, of course. Remember, if you have many parameters, you need to have a lot of data to set them up. 2 parameters, at least 2 data points, many parameters, many data points. So you need to have a model that is complex enough to express your decision, but in order to train this model so that the parameters are fixed, you need to have a lot of training data. What's interesting with this simple picture here is that, I'll show maybe visually, as you go through the layers of a neural network, the model starts being able to picking up patterns that are more and more complicated. So here is an example. You have here 3 layers. It's been fed with images and input. And I'll show you what the first layer reacts to. It's the first box on the left. And you see nothing that a human eye can recognize. It's very universal. These are prototype edges that you would find in any image. It's not very expressive. But as you go through the next layer, in the middle, you start seeing patterns like curved things, textures. And if you go to the 3rd layer, you start seeing shapes. That's very interesting because by combining these shapes, you can come up with images. For instance, you see here that some of the neurons have probably been exposed to pictures where there were birds, and they start to be particularized to the head of a bird. Or you see, if you want to go on the top, you see part of a wheel of a car. And so, by just fitting this model, you see that the system has been able to pick up parts of a car, and it becomes easy for the system to recognize if there is a car in an image or not. But you have not instructed the model to learn a model of a car. You've just exposed it to many examples of cars. So, the first layers in such a deep model are completely generic. The last layers are less generic, more specific to the data that you have used. This is going to be interesting because you can train these many parameters on some generic data set, but then you can freeze the parameters that pertain only to the first layers and particularize them to your data. This is a technique we'll be talking about, I guess, which is called fine-tuning. All right, so let's go back to this. So, machine learning in general, and again, it's a very blunt and summarized version of it, is this idea that you can model a decision by setting up a model that has many parameters, and you need to have a lot of training data to set the parameters. The best example I could give you is down here. Suppose you want to do what your phone does, recognize faces in an image. You will set up a model, you will pick up a neural network, and in order to set the parameters, you need to gather training data. The training data is pairs. An image with the label, there is a face. Another image with a label, there is no face. And you need sufficiently many pairs like that to set up the parameters of your neural network. Once trained, once the parameters are set, the neural network becomes extremely good at detecting whether or not there is a face in an image. And your phone does that. 15 years ago, your phone was trying to pick up faces of people by explicitly modeling what a face is. Well, it's something oval, there is that gamut of colors in the human pigmentation, there's 2 eyes most of the time, maybe a mouth. It was very, very complicated. Here we just completely abandoned this idea of explicitly modeling reality and replacing it by, we have a model and we give example of reality. What on earth is the model selecting to detect that there is a face? I don't know, and nobody does. All right, good. Generative AI now. There's many ways of seeing generative AI. I'll just give you one version of it, or 2 versions of it, sorry. First is generation of images. I'll give the example of what's called generative adversarial networks because it's easier, but there's many other more efficient techniques now. So suppose we've done just that. We've trained a neural network at recognizing faces. So it's very good at saying this is a face or not. Okay, it's been trained. And now I come up with another network, and I will ask this network to make images. For that, I will give it a random image at the input, and I will say, I will ask the neural net to modify the values of the pixels so that the output looks like a human face. But of course, that second neural network doesn't know at all what a human face is, so it's going to do garbage. But I'm going to send back this garbage to the first neural network and ask that neural network, is this a face? Now, that neural network is very good at saying, this is not a face. It's going to send back this information to the second one and ask it to update its parameters. And the game is going to be played between these two up to the moment the second one is able to output images that are good enough to fool the first one. So again, none of these two guys knows what a face is. You're not going to be able, most of the time, to identify how it models an eye, a nose, or a mouth. But there's many parameters in that model. It's sufficiently good at taking input noise, changing it so that the output is able to fool the first one. That's all they do. But by playing this game, this happens. Right? None of these people exist on the planet. They've been completely synthesized by this little game. And you can even cross the features of an image of one generated image with another one to generate even more versatility. So you can use that at scale to create, fake profiles of chatbots, for instance. All right, so that's generative AI for images. Could be the same for sound, for instance. Now, for text, we are going into the realm of what's called large language models. Slightly different beast. Again, in 1 minute now, what's a large language model? So you've heard about ChatGPT. GPT stands for Generalized Pre-trained Transformer. So transformer is a type of neural network. So you know what that is. It's going to be a neural network type of model, specifically geared at text. It's going to learn representation of words, what we call tokens, so about the same thing as words, and in a very interesting way. So it's going to take a large corpus of text, for instance, sentences like this one, a quick brown fox jumps over the lazy dog. And it's simply going to be trained at taking one decision. You're going to remove words in this. For instance, you're going to remove the word quick. And based on the words that remain, so based on the context, you are going to ask the neural network to predict, take the decision of predicting what is the missing word. The funny thing, please note, is that you don't need to have labeled data. Nobody needs to say it is the word quick. The system has access to this sentence anyway, so it can mask, blank out words at random, and train itself at predicting what's missing based on what it sees. When it becomes very, very good at predicting this missing word based on the context, it has become very, very good at understanding that language or generating sentences in that language. And how does it generate a sentence? It's going to generate sentences in an autoregressive way, which simply means you start with a word, it's going to predict the next one, then from these two words, the next one, then from these three words, the next one, and so forth. You can start with half a sentence, ask it to continue. You can start randomly with a word, ask it to continue. And the system is going to, word by word, that's important. This is still what language systems do. In an autoregressive way, word by word, predict the next word in the sentence. The system that ChatGPT was using at first, GPT-3, is a neural net, a transformer model, with 175 billion parameters. That's a lot of parameters to set, so you need access to huge corpus of data to set that many parameters. So Wikipedia, for instance, is just 0.6% of GPT-3's training set. And that's one of the issues we can maybe discuss in the panel. All right, now that's ChatGPT. ChatGPT is a beast on top of that. So the backbone is a large pre-trained language model, something that has been pre-trained on large corpus of text to be able to output, predict the next word in a sentence. So that's trained once and for all in an unsupervised way. You don't even have to look at it. Then ChatGPT is some sort of fine-tuned for conversational interactions. That's the chat part. And there's a funky bit of technicality in there. So it's fine-tuned using something called reinforcement learning with human feedback, which is interesting to know. And roughly speaking, it does the following. A system like that, when it interacts with a human being, can propose several answers to a question. So the system has to decide what is the best way to answer. So how is this done? Well, it first interacted with human beings who ranked the answers the system were giving. And then the system learned to do this ranking by himself. So every time you interact with ChatGPT, there is a little module that the system uses to rank its own answers so that it pleases to a human interactor. All right. Okay. It works very well, but I hear every so often that it's able to do reasoning, and it's as intelligent or maybe more intelligent than a person. You can easily fool this system, still today. You can have this kind of conversation where the system would have to reason about a family, for instance, and the members of a family. It gives perfectly confident, super nicely formatted answers which are completely wrong. And remember, there's a good reason for that. It's not trained to reason, it's trained to predict the next word in a sentence. I went this morning and I did this simple thing, ask it to multiply two numbers of size 4. Something you can do, something a kid can do. All right, so 3,567 by 2,063. You can do that with a piece of paper, you can do that with your phone, or a little pocket calculator with no mistake. It cannot do that this morning, the free version, okay? Which is interesting. If you try to give it cues that it made a mistake, it's going to pick up the cues but still make a mistake. All right, so that's also interesting. And what's fascinating, nevertheless, is that it's not far off. So somehow it has picked up the pattern that by multiplying numbers of this size, the output should be of that size. And that when you multiply numbers that finishes by 7 by 3 and 7, sorry, the final number should finish by 1. It always gives you an answer that finishes by 1. But still, it always gives you bad answer. So in this debate whether or not we are going to be taken over by superhuman AI, this is a superhuman AI which I think would just die in 1 minute if it's left alone in nature. It's going to synthesize something that doesn't work and blow up. All right, outlook, and I'll finish by that. Maybe important for the panel. So why does it all work? It works because of that, and nothing else in my views. We produce a lot of data. You can go and see this little picture every year. This is data that you give freely on your own will to Google, Meta, etc. A lot of it. And a lot of it because a sizable fraction of humans now have access to internet via fixed or mobile, mostly mobile these days. And the amount of digital data that we put out there is just staggering. So that's training data that some can use. And when I say some, not all. Right? It's been very well reflected by what our economy has become in the last 15 years, for instance. So that's also something maybe to keep in mind when we think about regulation. The question is not, nowadays, must we regulate, but how? Right? Because this is going very far now. And this is going to be going quicker and quicker, because as you can see, the rate of increase of the size of these models is exponential. This is on a log scale. There's virtues to that. All electronics gadgets we have are thanks to an exponential scaling law, Moore's law. All fantastic AI products we have and will have is thanks to, at the moment, an exponential scaling law, which is this one. But the actors that are able to control that are few. And of course, when we regulate, also keep in mind, they can do extremely complex things, but like in this example where a system was completely full to classify all images as ostriches, it's also very brittle, and people don't speak too much about that in the news. It's also very important to keep in mind. Thank you very much.